Welcome to the channel NextGen Tech Prep. In today's video, we are diving deep into essential questions and comprehensive answers for the Google Professional Machine Learning Engineer certification. Whether you're preparing for an exam or just looking to sharpen your knowledge, you're in the right place. If you find this content valuable, please hit that subscribe button and ring the notification bell so you never miss an update. Now, let's get started.
You are developing an ML pipeline using Vertex AI pipelines. You want your pipeline to upload a new version of the XGBoost model to Vertex AI model registry and deploy it to Vertex AI endpoints for online inference. You want to use the simplest approach. What should you do? The options are: Option A, use the Vertex AI REST API within a custom component based on a Vertex AI/prediction/boost CPU image. Option B, use the Vertex AI Model Evaluation Op component to evaluate the model. Option C, use the Vertex AI SDK for Python within a custom component based on a Python 3.10 image. Option D, chain the Vertex AI Model Upload Op and Model Deploy Op components together.
To arrive at the correct answer, we focus on the keywords: Vertex AI pipelines, upload a new version of the XGBoost model to Vertex AI model registry, deploy it to Vertex AI endpoints, simplest approach.
The correct answer is option D, chain the Vertex AI Model Upload Op and Model Deploy Op components together.
Why is this correct? D. Google Cloud Pipeline components provide pre-built Vertex AI components like Model Upload Op and Model Deploy Op. This is the simplest and recommended approach to upload and deploy models without writing custom code. Why are the others incorrect? A. Using the REST API within a custom component requires writing custom code to handle authentication and API requests, which contradicts the requirement for the simplest approach. B. Model Evaluation Op is used solely for evaluating the performance of models, not for uploading them to the model registry or deploying them to endpoints. C. Using the Vertex AI SDK in a custom component requires writing and maintaining custom Python code, making it more complex than using the out-of-the-box pre-built components.
You work at a mobile gaming startup that creates online multiplayer games. Recently, your company observed an increase in players cheating in the games, leading to a loss of revenue and a poor user experience. You built a binary classification model to determine whether a player cheated after a completed game session, and then send a message to other downstream systems to ban the player that cheated. Your model has performed well during testing, and you now need to deploy the model to production. You want your serving solution to provide immediate classifications after a completed game session to avoid further loss of revenue. What should you do? The options are: Option A, import the model into Vertex AI model registry. Use the Vertex batch prediction service to run batch inference jobs. Option B, save the model files in a cloud storage bucket. Create a cloud function to read the model files and make online inference requests on the cloud function. Option C, save the model files in a VM. Load the model files each time there is a prediction request, and run an inference job on the VM. Option D, import the model into Vertex AI model registry. Create a Vertex AI endpoint that hosts the model, and make online inference requests.
To arrive at the correct answer, we focus on the keywords: deploy the model to production, immediate classifications.
The correct answer is option D, import the model into Vertex AI model registry. Create a Vertex AI endpoint that hosts the model, and make online inference requests.
Why is this correct? D. Vertex AI model registry and endpoints provide a fully managed, scalable solution purpose-built for deploying models and serving real-time, online predictions, perfectly matching the requirement for immediate classifications. Why are the others incorrect? A. Vertex batch prediction is designed for asynchronous, offline processing of large datasets, which does not meet the requirement for real-time or immediate classifications. B. Cloud functions are not optimized for ML model serving, they lack the specialized infrastructure, performance tuning, and management features inherent to Vertex AI endpoints. See, managing models on a raw VM and loading them on each request is inefficient, hard to scale, and requires significant operational overhead compared to a managed service.
You are investigating the root cause of a misclassification error made by one of your models. You used Vertex AI pipelines to train and deploy the model. The pipeline reads data from BigQuery, creates a copy of the data in cloud storage in TF record format, trains the model in Vertex AI training on that copy, and deploys the model to a Vertex AI endpoint. You have identified the specific version of that model that misclassified, and you need to recover the data this model was trained on. How should you find that copy of the data? The options are: Option A, use Vertex AI Feature Store. Modify the pipeline to use the feature store, and ensure that all training data is stored in it. Search the feature store for the data used for the training. Option B, use the lineage feature of Vertex AI metadata to find the model artifact. Determine the version of the model and identify the step that creates the data copy and search in the metadata for its location. Option C, use the logging features in the Vertex AI endpoint to determine the timestamp of the model's deployment. Find the pipeline run at that timestamp. Identify the step that creates the data copy, and search in the logs for its location. Option D, find the job ID in Vertex AI training corresponding to the training for the model. Search in the logs of that job for the data used for the training.
To arrive at the correct answer, we focus on the keywords: Vertex AI pipelines, identified the specific version, recover the data this model was trained on.
The correct answer is option B, use the lineage feature of Vertex AI metadata to find the model artifact. Determine the version of the model and identify the step that creates the data copy and search in the metadata for its location.
Why is this correct? B. Vertex AI metadata automatically tracks the lineage of artifacts, including inputs and outputs of pipeline steps. This allows you to trace a specific model version back to the exact cloud storage copy it was trained on. Why are the others incorrect? A. Vertex AI Feature Store manages features, not raw dataset copies in cloud storage. Modifying the pipeline won't help you recover data for a model that has already been trained and deployed. C. Tracing lineage via deployment timestamps and parsing logs is a manual, error-prone, and inefficient process. Vertex AI metadata is explicitly designed to solve this exact artifact tracking problem. D. Manually parsing Vertex AI training job logs for data locations is highly inefficient. Vertex ML metadata provides built-in lineage tracking to effortlessly link models back to their training data artifacts.
You work at a bank. You need to develop a credit risk model to support loan application decisions. You decide to implement the model by using a neural network in TensorFlow. Due to regulatory requirements, you need to be able to explain the model's predictions based on its features. When the model is deployed, you also want to monitor the model's performance over time. You decided to use Vertex AI for both model development and deployment. What should you do? The options are: Option A, use Vertex Explainable AI with the sampled Shapley method, and enable Vertex AI model monitoring to check for feature distribution drift. Option B, use Vertex Explainable AI with the sampled Shapley method, and enable Vertex AI model monitoring to check for feature distribution skew. Option C, use Vertex Explainable AI with the XRAI method, and enable Vertex AI model monitoring to check for feature distribution drift. Option D, use Vertex Explainable AI with the XRAI method, and enable Vertex AI model monitoring to check for feature distribution skew.
To arrive at the correct answer, we focus on the keywords: credit risk model, explain the model's predictions based on its features, monitor the model's performance over time.
The correct answer is option A, use Vertex Explainable AI with the sampled Shapley method, and enable Vertex AI model monitoring to check for feature distribution drift.
Why is this correct? A sampled Shapley is the appropriate attribution method for tabular feature data like a credit risk model. Monitoring feature distribution drift is the correct approach to track changes in serving data over time. Why are the others incorrect? B. Feature distribution skew compares production data to training data, which does not address the requirement to monitor performance changes over time. C. XRAI is an attribution method designed specifically for image data and is not suitable for explaining tabular features in a credit risk model. D. XRAI is intended for image data, and feature distribution skew checks for training serving differences rather than monitoring changes over time.
Your team is training a large number of ML models that use different algorithms, parameters, and datasets. Some models are trained in Vertex AI pipelines, and some are trained on Vertex AI Workbench notebook instances. Your team wants to compare the performance of the models across both services. You want to minimize the effort required to store the parameters and metrics. What should you do? The options are: Option A, implement an additional step for all the models running in pipelines and notebooks to export parameters and metrics to BigQuery. Option B, create a Vertex AI experiment. Submit all the pipelines as experiment runs. For models trained on notebooks, log parameters and metrics by using the Vertex AI SDK. Option C, implement all models in Vertex AI pipelines. Create a Vertex AI experiment and associate all pipeline runs with that experiment. Option D, store all model parameters and metrics as model metadata by using the Vertex AI Metadata API.
To arrive at the correct answer, we focus on the keywords: Vertex AI pipelines, Vertex AI Workbench notebook instances, compare the performance of the models across both services, minimize the effort required to store the parameters and metrics.
The correct answer is option B, create a Vertex AI experiment. Submit all the pipelines as experiment runs. For models trained on notebooks, log parameters and metrics by using the Vertex AI SDK.
Why is this correct? B. Vertex AI experiments natively tracks parameters and metrics. Pipelines can automatically log to an experiment. The Vertex AI SDK enables easy logging from Workbench notebooks, providing a centralized, low-effort way to compare models. Why are the others incorrect? A. Exporting manually to BigQuery requires writing custom code to format and write the data, violating the requirement to minimize effort when built-in tracking exists. C. Rewriting all notebook models into Vertex AI pipelines significantly increases engineering effort, violating the core requirement to minimize effort. D. While Vertex ML metadata is the underlying service, interacting with the metadata API directly requires more custom code and effort compared to using Vertex AI experiments.
You work for an organization that operates a streaming music service. You have a custom production model that is serving a next song recommendation based on a user's recent listening history. Your model is deployed on a Vertex AI endpoint. You recently retrained the same model by using fresh data. The model received positive test results offline. You now want to test the new model in production while minimizing complexity. What should you do? The options are: Option A, create a new Vertex AI endpoint for the new model and deploy the new model to that new endpoint. Build a service to randomly send 5% of production traffic to the new endpoint. Monitor end-user metrics such as listening time. If end-user metrics improve between models over time, gradually increase the percentage of production traffic sent to the new endpoint. Option B, capture incoming prediction requests in BigQuery. Create an experiment in Vertex AI experiments. Run batch predictions for both models using the captured data. Use the user's selected song to compare the model's performance side by side. If the new model's performance metrics are better than the previous model, deploy the new model to production. And the remaining options are: Option C, deploy the new model to the existing Vertex AI endpoint. Use traffic splitting to send 5% of production traffic to the new model. Monitor end-user metrics, such as listening time. If end-user metrics improve between models over time, gradually increase the percentage of production traffic sent to the new model. Option D. Configure a model monitoring job for the existing Vertex AI endpoint. Configure the monitoring job to detect prediction drift and set a threshold for alerts. Update the model on the endpoint from the previous model to the new model. If you receive an alert of prediction drift, revert to the previous model.
To arrive at the correct answer, we focus on the keywords deployed on a Vertex AI endpoint, test the new model in production, minimizing complexity.
Review the options on screen. The correct answer is option C. Deploy the new model to the existing Vertex AI endpoint. Use traffic splitting to send 5% of production traffic to the new model. Monitor end-user metrics, such as listening time. If end-user metrics improve between models over time, gradually increase the percentage of production traffic sent to the new model.
Why is this correct? C. Deploying to the existing Vertex AI endpoint and using its native traffic splitting feature allows you to test the model in production while minimizing complexity, avoiding custom routing services. Why are the others incorrect? A. Building a custom service to route traffic to a new endpoint introduces unnecessary complexity, as Vertex AI endpoints already natively support traffic splitting. B. Capturing requests and running batch predictions is an offline evaluation method, which fails the requirement to test the new model in production. D. Configuring model monitoring is for observing prediction drift over time, not a deployment strategy for testing a new model with live production traffic.
You work on the data science team at a manufacturing company. You are reviewing the company's historical sales data, which has hundreds of millions of records. For your exploratory data analysis, you need to calculate descriptive statistics such as mean, median, and mode, conduct complex statistical tests for hypothesis testing, and plot variations of the features over time. You want to use as much of the sales data as possible in your analyses while minimizing computational resources. What should you do? The options are: Option A, visualize the time plots in Google Data Studio. Import the dataset into Vertex AI Workbench user-managed notebooks. Use this data to calculate the descriptive statistics and run the statistical analyses. Option B, spin up a Vertex AI Workbench user-managed notebooks instance and import the dataset. Use this data to create statistical and visual analyses. Option C, use BigQuery to calculate the descriptive statistics. Use Vertex AI Workbench user-managed notebooks to visualize the time plots and run the statistical analyses. Option D, use BigQuery to calculate the descriptive statistics, and use Google Data Studio to visualize the time plots. Use Vertex AI Workbench user-managed notebooks to run the statistical analyses.
To arrive at the correct answer, we focus on the keywords, hundreds of millions of records, calculate descriptive statistics, conduct complex statistical tests, plot variations of the features over time, minimizing computational resources.
The correct answer is option C. Use BigQuery to calculate the descriptive statistics. Use Vertex AI Workbench user-managed notebooks to visualize the time plots and run the statistical analyses.
Why is this correct? C. BigQuery efficiently handles descriptive statistics on hundreds of millions of records without moving data, minimizing computational resources. Vertex AI Workbench provides the necessary Python environment for complex statistical testing and visualizing time plots during exploratory data analysis. Why are the others incorrect? A. Importing hundreds of millions of records into a notebook instance to compute basic descriptive statistics is highly inefficient and would require excessive computational resources in memory. B. Pulling the entire massive dataset directly into a Vertex AI Workbench notebook for statistical analysis is computationally expensive and scales poorly compared to utilizing BigQuery. Why are the others incorrect? D. While using BigQuery for statistics is correct, Splitting the exploratory data analysis workflow by using Data Studio solely for visualizations adds unnecessary tool switching when notebooks can seamlessly handle both plots and complex tests.
You work for a rapidly growing social media company. Your team builds TensorFlow recommender models in an on-premises CPU cluster. The data contains billions of historical user events and 100,000 categorical features. You notice that as the data increases, the model training time increases. You plan to move the models to Google Cloud. You want to use the most scalable approach that also minimizes training time. What should you do? The options are: Option A, deploy the training jobs by using TPU VMs with TPU v3 pod slices, and use the TPU embedding API. Option B, deploy the training jobs in an auto-scaling Google Kubernetes engine cluster with CPUs. Option C, deploy a matrix factorization model training job by using BigQuery ML. Option D, deploy the training jobs by using compute engine instances with a 100 GPUs, and use the tf.nn.embedding_lookup API.
To arrive at the correct answer, we focus on the keywords: TensorFlow recommender models, billions of historical user events, 100,000 categorical features, most scalable approach, minimizes training time.
The correct answer is option A, deploy the training jobs by using TPU VMs with TPU v3 pod slices, and use the TPU embedding API.
Why is this correct? A. TPU embedding API is purpose-built to accelerate massive embedding lookups common in recommender models with numerous categorical features. TPU v3 pod slices provide massive distributed compute, perfectly satisfying the requirement for the most scalable approach that minimizes training time. Why are the others incorrect? B. CPUs are highly inefficient for training deep learning models on large datasets with massive embeddings. This approach will be significantly slower than using specialized hardware accelerators like TPUs, failing to minimize training time. C. BigQuery ML matrix factorization is designed for simpler collaborative filtering tasks but lacks the flexibility and advanced deep learning capabilities necessary to run complex, custom TensorFlow recommender models natively. Why are the others incorrect? D. While a 100 GPUs are powerful, managing extremely large embedding tables using standard tf.nn.embedding_lookup is less scalable than using the specialized TPU embedding API on TPU pods, which is explicitly optimized for distributed embeddings.
You developed a custom model by using Vertex AI to predict your application's user churn rate. You are using Vertex AI model monitoring for skew detection. The training data stored in BigQuery contains two sets of features: demographic and behavioral. You later discover that two separate models trained on each set perform better than the original model. You need to configure a new model monitoring pipeline that splits traffic among the two models. You want to use the same prediction sampling rate and monitoring frequency for each model. You also want to minimize management effort. What should you do? The options are: Option A, keep the training dataset as is. Deploy the models to two separate endpoints, and submit two Vertex AI model monitoring jobs with appropriately selected feature thresholds parameters. Option B, keep the training dataset as is. Deploy both models to the same endpoint and submit a Vertex AI model monitoring job with a monitoring config from file parameter that accounts for the model IDs and feature selections. Option C, separate the training dataset into two tables based on demographic and behavioral features. Deploy the models to two separate endpoints, and submit two Vertex AI model monitoring jobs. Option D, separate the training dataset into two tables based on demographic and behavioral features. Deploy both models to the same endpoint, and submit a Vertex AI model monitoring job with a monitoring config from file parameter that accounts for the model IDs and training datasets.
To arrive at the correct answer, we focus on the keywords. Vertex AI model monitoring splits traffic among the two models, same prediction sampling rate and monitoring frequency, minimize management effort.
The correct answer is option B, keep the training dataset as is. Deploy both models to the same endpoint and submit a Vertex AI model monitoring job with a monitoring config from file parameter that accounts for the model IDs and feature selections.
Why is this correct? B. Deploying both models to the same endpoint enables traffic splitting. Using a single monitoring config from file configures monitoring for multiple models on one endpoint without altering the dataset, minimizing management effort. Why are the others incorrect? A. Deploying to two separate endpoints and submitting two separate monitoring jobs significantly increases management effort compared to using a single endpoint. C. Separating the training dataset and using two separate endpoints introduces unnecessary data duplication and operational overhead, failing to minimize management effort. D. Separating the training dataset into two tables is unnecessary data management overhead. The monitoring config file can specify which features to monitor from the unified dataset.
You are developing ML models with AI platform for image segmentation on CT scans. You frequently update your model architectures based on the newest available research papers, and have to rerun training on the same dataset to benchmark their performance. You want to minimize computation costs and manual intervention while having version control for your code. What should you do? The options are: Option A, use cloud functions to identify changes to your code in cloud storage and trigger a retraining job. Option B, use the cloud command line tool to submit training jobs on AI platform when you update your code. Option C, use cloud build linked with cloud source repositories to trigger retraining when new code is pushed to the repository. Option D, create an automated workflow in Cloud Composer that runs daily and looks for changes in code in cloud storage using a sensor.
To arrive at the correct answer, we focus on the keywords: minimize computation costs, manual intervention, version control for your code.
The correct answer is option C, use cloud build linked with cloud source repositories to trigger retraining when new code is pushed to the repository.
Why is this correct? C. Cloud source repositories provides version control for your code. Cloud build automates retraining triggers upon code push, minimizing manual intervention. It also minimizes computation costs by only running when triggered, unlike continuous polling methods. Why are the others incorrect? A. Cloud storage is an object storage service, not a version control system. While it has object versioning, it lacks the standard features expected for proper version control of code. B. Manually submitting training jobs using the cloud command line tool requires significant manual intervention for every code update, directly contradicting the requirement to minimize it. Why are the others incorrect? D. Cloud storage does not provide proper code version control. Additionally, running a daily Cloud Composer workflow with a sensor incurs unnecessary compute costs for polling and delays training execution.
You work for a public transportation company and need to build a model to estimate delay times for multiple transportation routes. Predictions are served directly to users in an app in real time. Because different seasons and population increases impact the data relevance, you will retrain the model every month. You want to follow Google recommended best practices. How should you configure the end-to-end architecture of the predictive model? The options are: Option A, configure Kubeflow pipelines to schedule your multi-step workflow from training to deploying your model. Option B, use a model trained and deployed on BigQuery ML, and trigger retraining with the scheduled query feature in BigQuery. Option C, write a Cloud Functions script that launches a training and deploying job on AI platform that is triggered by Cloud Scheduler. Option D, use Cloud Composer to programmatically schedule a Dataflow job that executes the workflow from training to deploying your model.
To arrive at the correct answer, we focus on the keywords, served directly to users in an app in real time, retrain the model every month, Google recommended best practices, end-to-end architecture.
The correct answer is option A. Configure Kubeflow pipelines to schedule your multi-step workflow from training to deploying your model.
Why is this correct? A. Kubeflow pipelines is the Google recommended standard for orchestrating end-to-end machine learning workflows, providing robust automation, scheduling, and tracking from model training to deployment. Why are the others incorrect? B. BigQuery ML is optimized for batch predictions and SQL-centric data processing, making it unsuitable for serving low-latency predictions directly to an app in real time. C. Relying on cloud functions in Cloud Scheduler lacks the robust multi-step pipeline orchestration, reproducibility, and metadata tracking capabilities that Google recommends for ML architectures. D. Dataflow is designed for large-scale data processing and ETL tasks, not for orchestrating complete ML lifecycles such as model training and deployment.
You recently built the first version of an image segmentation model for a self-driving car. After deploying the model, you observe a decrease in the area under the curve (AUC) metric. When analyzing the video recordings, you also discover that the model fails in highly congested traffic but works as expected when there is less traffic. What is the most likely reason for this result? The options are: Option A. The model is overfitting in areas with less traffic and underfitting in areas with more traffic. Option B. AUC is not the correct metric to evaluate this classification model. Option C. Too much data representing congested areas was used for model training. Option D. Gradients become small and vanish while backpropagating from the output to input nodes.
To arrive at the correct answer, we focus on the keywords, decrease in the area under the curve (AUC) metric, fails in highly congested traffic, works as expected when there is less traffic.
The correct answer is option A. The model is overfitting in areas with less traffic and underfitting in areas with more traffic.
Why is this correct? A. The model's good performance in less traffic and poor performance in highly congested traffic indicates it learned the simpler patterns, overfitting, but failed to capture the complexity of congested scenarios, underfitting, likely due to data imbalance. Why are the others incorrect? B. AUC is a valid metric for the classification aspect of image segmentation tasks, pixel-wise classification. It is not the reason for the model's failure in specific traffic conditions. C. If too much data representing congested areas was used, the model would likely perform well in those scenarios, which contradicts the observation that it fails in highly congested traffic. D. Vanishing gradients would prevent the model from learning effectively overall, leading to poor performance across all conditions, rather than failing selectively only in highly congested traffic.
You trained a model, packaged it with a custom Docker container for serving, and deployed it to Vertex AI model registry. When you submit a batch prediction job, it fails with this error: model server never became ready. Please validate that your model file or container configuration are valid. There are no additional errors in the logs. What should you do? The options are: Option A. Add a logging configuration to your application to emit logs to cloud logging. Option B. Change the HTTP port in your model's configuration to the default value of 8080. Option C. Change the health route value in your model's configuration to /healthcheck. Option D. Pull the Docker image locally, and use the Docker run command to launch it locally. Use the Docker logs command to explore the error logs.
To arrive at the correct answer, we focus on the keywords, custom Docker container, batch prediction job, error model server never became ready, no additional errors in the logs.
The correct answer is option D. Pull the Docker image locally, and use the Docker run command to launch it locally. Use the Docker logs command to explore the error logs.
Why is this correct? D. Running the container locally replicates the environment and provides direct access to startup logs, making it the most effective way to identify why the model server failed to start when Vertex AI logs are insufficient. Why are the others incorrect? A. Adding logging inside the application won't help if the container itself crashes during startup before the application's logging logic can execute. B. Assuming the port is incorrect without verifying the actual error in the container logs is premature and might not solve the underlying issue. C. Changing the health route is merely a guess. Without local logs, you cannot confirm if the health check configuration is actually the cause of the failure.
You are developing a training pipeline for a new XGBoost classification model based on tabular data. The data is stored in a BigQuery table. You need to complete the following steps. 1. Randomly split the data into training and evaluation datasets in a 65/35 ratio. 2. Conduct feature engineering. 3. Obtain metrics for the evaluation dataset. 4. Compare models trained in different pipeline executions. How should you execute these steps? The options are: Option A, 1. Using Vertex AI pipelines, add a component to divide the data into training and evaluation sets, and add another component for feature engineering. 2. Enable autologging of metrics in the training component. 3. Compare pipeline runs in Vertex AI experiments. Option B, 1. Using Vertex AI pipelines, add a component to divide the data into training and evaluation sets, and add another component for feature engineering. 2. Enable autologging of metrics in the training component. 3. Compare models using the artifacts lineage in Vertex ML metadata. Option C, 1. In BigQuery ML, use the create model statement with boosted_tree_ classifier as the model type and use BigQuery to handle the data splits. 2. Use a SQL view to apply feature engineering and train the model using the data in that view. 3. Compare the evaluation metrics of the models by using a SQL query with the ml.training_info statement. And the remaining options are: Option D, 1. In BigQuery ML, use the create model statement with boosted_tree_ classifier as the model type and use BigQuery to handle the data splits. 2. Use ML transform to specify the feature engineering transformations and tram the model using the data in the table. 3. Compare the evaluation metrics of the models by using a SQL query with the ml.training_info statement.
To arrive at the correct answer, we focus on the keywords: training pipeline, 65/35 ratio, compare models trained in different pipeline executions.
The correct answer is option A, 1. Using Vertex AI pipelines, add a component to divide the data into training and evaluation sets, and add another component for feature engineering. 2. Enable autologging of metrics in the training component. 3. Compare pipeline runs in Vertex AI experiments. Review the options on screen.
Why is this correct? A. Vertex AI pipelines accommodates custom data splitting and feature engineering components. Vertex AI experiments is explicitly designed to track and compare parameters and metrics across multiple pipeline runs, satisfying the model comparison requirement. Why are the others incorrect? B. Vertex ML metadata is designed for tracking artifact lineage and metadata, not for providing a built-in interface to compare evaluation metrics across different pipeline runs. C. The ml.training_info statement returns information about the training iterations of a single model, making it unsuitable for comparing metrics across different models from various pipeline executions. D. Similar to option C, ml.training_info only inspects a single model's training history and is not the correct approach for comparing multiple models trained in different executions.
You are building a TensorFlow model for a financial institution that predicts the impact of consumer spending on inflation globally. Due to the size and nature of the data, your model is long-running across all types of hardware, and you have built frequent checkpointing into the training process. Your organization has asked you to minimize cost. What hardware should you choose? The options are: Option A, a Vertex AI Workbench user-managed notebooks instance running on an N1 Standard 16 with 4 NVIDIA P100 GPUs. Option B, A Vertex AI Workbench user-managed notebooks instance running on an N1 Standard 16 with an NVIDIA P100 GPU. Option C. A Vertex AI Workbench user-managed notebooks instance running on an N1 Standard 16 with a non-preemptible V3-8 TPU. Option D. A Vertex AI Workbench user-managed notebooks instance running on an N1 Standard 16 with a preemptible V3-8 TPU.
To arrive at the correct answer, we focus on the keywords, TensorFlow model, frequent checkpointing, minimize cost.
Correct answer is option D. A Vertex AI Workbench user-managed notebooks instance running on an N1 Standard 16 with a preemptible V3-8 TPU.
Why is this correct? D. Preemptible TPUs offer the lowest cost for TensorFlow workloads. Since the training process includes frequent checkpointing, the risk of preemption is mitigated, making this the most cost-effective choice. Why are the others incorrect? A. Standard GPUs are more expensive than preemptible TPUs, and provisioning for GPUs does not align with the primary goal of minimizing cost. B. A standard, non-preemptible GPU is more expensive than a preemptible TPU and does not leverage the frequent checkpointing to save costs. C. Non-preemptible TPUs are significantly more expensive than preemptible TPUs. Given the frequent checkpointing, paying the premium for non-preemptible hardware is unnecessary.